Hello and welcome to this lecture. So we've seen already a definition for linear transformation in R2 and then how a matrix 2 by 2 matrix actually represents a linear transformation in terms of what happens to basis vector when you do the linear transformation and you represent each column of the matrix with the transformed vector, right? So let's see how to do that for the two examples we saw, the rotation and scaling example. Both of these are linear transformations, and it turns out they can be represented by matrices, and we're going to see how to do that in this lecture. Okay. The first is scaling. This is the simplest forms of scaling, where I take a vector u, which is xy in R2, and then the linear transformation T of u is simply scaling of this vector by alpha. In the same direction, you scale by alpha. So both the x coordinate and the y coordinate get multiplied by alpha, right? So this, what does this transformation do? It takes an xy and makes it alpha x, alpha y, depending on what alpha is. Okay. So now, if you want to see it pictorially in the xy sort of axis and the plane, if you look at 1 0, which is the E1, the canonical basis vector, the first basis vector. If you multiply, if you do T of 1 0, you're going to get alpha 0. So the first column of the matrix representation with respect to the canonical basis is alpha 0. Okay, the same thing. Now if you look at 0 1, that through this transformation of scaling will become 0 alpha. Okay, just multiply this with alpha, right? 0 is just 0, 1 multiplied by alpha is alpha, and then the second column now of this matrix will become 0 alpha. Okay, so this alpha 0 0 alpha read row wise, or alpha 0 0 alpha read column wise, this is my matrix representing the scaling by alpha, where the vector itself is getting scaled. Both axes are getting scaled by the same quantity. Easy, isn't it? So these kind of examples are very easy to figure out what the matrix should be. Okay. Now here is a non-symmetric scaling, where I take a u in xy, and then my transformation scales the x-axis differently and the y-axis differently. So x is getting scaled by alpha 1, slightly larger value here, and then y is getting scaled by alpha 2, which maybe is a smaller value here, right? So now what happens to 1 0? It goes to alpha 1 0. So my column vector is alpha 1 0, and then 0 1 goes to 0 alpha 2. So you get 0 alpha 2 in this way. Okay. So I hope this is easy enough, right? So even if you have non-symmetric scaling, alpha 1, alpha 2, matrix is easy to figure out. So both of these, you see, a non-zero value comes only in the diagonal of this matrix, the diagonal part here, and the non-diagonal is 0. Okay, easy enough. So let's move to rotation. Okay, so I'm going to talk about this transform T, which is a rotation, anti-clockwise rotation by an angle theta naught. Okay, so in polar coordinates, we know this is easy to describe. U is r theta, then T of u is simply r comma theta plus theta naught. Now what happens to the basis vectors? The canonical basis vectors 1 0 now is getting rotated by an angle theta naught, and you get this red, right? So from blue white you went to red. So this is theta naught. So from here we can figure out what the coordinates of this point are, right? So we know this will be cos theta naught. See, this is 1, right? So this hypotenuse is also 1. So this length will be cos theta naught, and this length will be sin theta naught, using our familiar trigonometric functions. Okay, so that is the coordinate cos theta naught, sin theta naught. So if you were to do a matrix, the first column of the matrix is going to be cos theta naught, sin theta naught. What about 0 1? What happens to 0 1? So it also gets rotated, and this angle now will become theta naught, and this length is 1. So the y coordinate now is cos theta naught, and the x coordinate now is minus sin theta naught, right? Minus sin theta naught goes in this direction. So just by looking at what happens to the basis vectors very easily through this rotation by theta naught, you see that the matrix of T with respect to the canonical basis is cos theta naught, sin theta naught in the first column, and minus sin theta naught, cos theta naught in the second column. So this is rotation. Okay. So any simple transformation like this, scaling possibly asymmetrically and rotation, is easy enough to describe in a matrix format and represent it that way. I hope this is clear.